This is the display interface of the Apollo 11 computers. This is the mission that took man to the moon. Now, the Apollo 11 computers were used by the astronauts, and they had to be especially trained so that they could enter commands using 2 digits. And the first digit was the verb, what was it to be performed, and the second one was the noun, what kind of data would be affected by the verb. Now, if you contrast this interface and the Apollo 11 computers with a modern smartphone like the iPhone 5, you're going to find some starking differences. And the iPhone 5 is 1,270 times faster than the Apollo 11 computers. It has 2 million times more processing memory, more storage memory, and it is also about 300 times lighter than the Apollo 11 computers. Now, I hope you can appreciate how much computational power you are carrying with you when you're walking about today. But I will leave it up to you to decide whether your smartphone can actually take you to the moon. And you are able to use one of these devices simply because of the acceleration in technologies that we have seen in the last few years. And especially Moore's law applies, and it suggests that nearly every 2 years, the number of transistors on integrated circuits basically doubles. So you can imagine why we have so much powerful machines. It is said that in the developed world, we are spending about 11 hours processing information on a daily basis. So whatever we do leaves a digital trail. When you walk around with when you walk around with a mobile phone, then we can track where you are with the GPS data. When you go to your doctor, you leave a digital record behind. When you interact through Facebook and Twitter, you generate content yourself, and some of you may be generating content even as we speak. When you purchase items on Amazon, then we know that you like science fiction movies. And when you go to the when I go to my supermarket knows that I like cheese and chocolate, but obviously not at the same time. So the amounts of information that we are creating increasing at an amazing speed. It is said that between 2010 and 2012, we have actually created more information than in all the years up to our past history. And it's quite interesting to see this with a very simple visualization. So if this is our recorded history, then 2010-12 are just about here. So you can imagine how much data we have generated just between those 2 years. In fact, it is estimated that every day we are producing about 2.5 billion gigabytes. That's a lot of information. That's millions, trillions of bytes that we are generating on a daily basis. In June 2014, Cisco updated their annual IP traffic projections for the next 5 years. And there are some interesting projections there. By 2018, the number of users that will be using the internet will be about 4 million. That's, in 2013, it was 2.5. And there are going to be about 21 billion networked devices by 2018. In 2013, there were about 12. And I will not even mention the staggering rate of information that will be exchanged through mobile phones, which by 2018 is going to reach 190 exabytes. In 2013, we only produced 18, so you can imagine how much information we are producing. And that brings us to big data, because it's clear that we generate a lot of data. And data are characterized by what they're called the V's. So we have volume. There's the sheer volume of data that are being produced. Velocity, the speed with which we are producing data, is absolutely astonishing. We do so in real time and from multiple sources. And variety. Data is not just structured, it can be unstructured, it can be social media data, content that you generate yourselves, it can be audio, video. So all of these increase complexity. And we are actually risking drowning in data. We have so much data that we don't really know how to process. Now, the assumption is if you have data, then you have knowledge. And if you have big data, therefore you have big knowledge. But this is not true. Data is not information, as Davenport says, and information is not knowledge, as Einstein says. Data is just recorded, they're just recorded transactions, structured transactions as they take place. Information results from the processing of the data, and it has meaning and shape. And then you have knowledge. And knowledge is what you are aiming for. You're trying to understand why things are happening. So in order to understand data, we perform data exploration. And data exploration is the analysis of data. So we are talking about techniques to analyze and interpret the data that we have at our disposal. And we use visualization if the data are particularly large data sets or complex data sets, because we would like to convey information to non-specialists in a way that will enable them to gain insight from the data. And modeling. And here we're talking about predictive modeling and validating and testing hypotheses. But ultimately, what we are after is value. The data is only valuable if we can extract useful insights from the data, if we are able to use it to inform decision-making that will be able, for instance, to inform decision-making in enterprises and businesses and other organizations. And it's this predictive aspect of modeling that I'm truly fascinated by. So if we start with big and complex data, then what we usually do is we analyze it, we interpret the data, and then we can use this analysis to inform our action and strategy. We can take it a step further, and then we can hypothesize as to why is it that we see these patterns emerging in the data. And we can stop here. But this is where I say, mind the gap. Because if you stop here just by formulating this theory, you're missing a unique opportunity to actually generate new knowledge, discover new knowledge. Because what we would like to do ideally is take it a step further, build models out of the assumptions, formulate assumptions as to why we see these patterns in the data, and then with these mathematical models or more complex types of models, we can try and validate our theory, our assumptions, and we can run these independent models, and we can generate artificial data sets, which we can then check against the real data that we see to check whether the same patterns emerge. And if the same patterns emerge, then you can say with some degree of confidence that your hypothesis is validated. When you have this kind of validation of your theory, you can imagine that you have a lot more confidence in your decision making, you can better inform your strategy, and you can support your action, no matter what organization you are. So I'm fascinated by these models that we can create based on the data that we may have at our disposal. So I'm going to tell you a couple of stories about how we can create such models and what kind of work we have been doing. I'm interested in complex models, not just any type of mathematical model. I'm interested in complex models that emanate from the tradition of artificial intelligence. And specifically, models that use agents and multi-agent systems. And the easiest way to explain what an agent is, from a computer science point of view, or an artificial point of view, is these independent software processes, if you like, that can act independently. They have their own functionality, and they have their own attributes. And then you can put them together in a scenario, in a simulated scenario, and they can start interacting with each other, and you can start observing what the outcome of their interaction is going to be at the system or the global level. Now, the interesting thing with these sort of models that I'm talking about is that you cannot predict them. It is not the case that we can encode within these agents their full behavior in such a way so that we know what the outcome is going to be. This is simply because in these complex systems, what you have is the final outcome only emerges as a result of the interaction of these independent entities, and you cannot predict how each one entity is going to affect the other. So these are the kind of entities that I'm interested in modeling. And we can code very complex behavior and functionality. We can encode things like trust or knowledge or beliefs that we usually ascribe to humans, for that matter. So have you seen this picture before? This is an image which has been created by Michael Najjar. Michael Najjar is an artist, and this is from his high altitude collection. And he went to Argentina to visit the mountain ranges there. And after that, he was inspired, and he created a series of images representing the evolution of the leading stock indices all around the world. And the image that you see in front of you is that of the evolution of the stock price of the Lehman Brothers from 92 up to 2008, and that's why you can see this very sharp drop, because it has basically crashed. Now, as you will notice, there are peaks and troughs in this image, and this is typical of financial data that we can gain from any financial market or this kind of environment. And these peaks and troughs are the result of interactions of thousands, literally thousands of trading agents, real trading agents, as well as artificial ones that are interacting within a financial market. Now, it's true that we can build what they're called algorithmic traders, algorithmic agents. So these are pieces of software that are able to identify patterns. They can look at this data, and with clever machine learning algorithms, they can identify patterns in the data and then make a decision as to whether to buy or to sell based on the movements that they can identify. But what these programs are not able to do is look to try and understand why we see these patterns emerging. And this is a fascinating question for me. This is what I'm interested in. What is it that makes these patterns emerge? What kind of behaviors do the agents, the trading agents, need to have? What characteristics, what strategies, so that we can see these patterns emerging? So I'm going to tell you about a project that we did. And we were able to obtain a very large data set of about 147 million transactions from about 45,000 traders on an anonymous basis from the financial, from the foreign exchange. So this is the market where you exchange currencies. And we are talking about a lot of data set, as you can see. So when you have this kind of data in the financial, in finance, you tend to deal with time series, and you tend to sample. So, and you can choose when to sample in the beginning, the end. You can do it at intervals and at random intervals. But when we talk about 147 million transactions, which were over 2 years, we are talking about 180,000 transactions per day. And if you attempt to sample, then you don't know when to sample, because you might miss a pattern by sampling at the wrong time. So we have a problem. How is it that we can process all this data? So in order to address this problem, instead of looking at this issue from a time series point of view, what we did was we attempted to identify events, directional change events in the data that we were seeing. And we formulated hypotheses after that as to why we were seeing some of these patterns and what kind of strategies the agents had behind. And then we built a very complex market, an artificial market, and we put in place there these agents, and I'm talking about thousands of agents that had their own strategies, and they started interacting with each other. And what you see here is just one of the results that we've had, and you see several lines in this particular graph. The line with the blue squares is the pattern identified in the real data. And when you look at the real data, and this has been identified by several studies, you see two humps when you look at the trading activity over a 24-hour period. The first hump is because you have the London market being open at the same time as the Asian market in the morning, and the second hump is because the London market is open at the same time as the American markets. And we ran various simulations with different sets of agents, with different strategies, and we were able to come up with a strategy that was able to bring the data very close to what we were observing in real life. And this is the one that has the red triangles. And so we were, to a certain extent, able to validate our hypothesis as to why we see these patterns in the data. When you're able to do that, the next step then is to try and do predictive modeling. So this is the next step coming in for us, and this is very exciting. Now, there are other domains that are equally fascinating, and they contain a lot of data. Not numerical data necessarily, but other types of data, such as, for instance, social networks. And social networks have increased so much in the last few years that it's absolutely extraordinary. And why do we engage in social networks? Well, it's our need to interact and communicate with each other, and social networks are guided by this principle of homophily. So what happens is we like to link with like-minded people, people that are like us. So this is called the principle of homophily. But within social networks, we make some assumptions as to what homophily is and how how humans find each other. And we wanted to transfer that to a modeling problem. And we were particularly interested in identifying how agents can start in a social network, and then how is it that they can identify each other? How is it that they can measure their similarity? And then by identifying other similar agents, how is it that they can create clusters? So we started with a network that had only one agent, and then we started putting in more agents. And what you're going to see now is the video that is going to play the simulation that we ran. And hopefully this is going to come up online anytime soon. Can we play the video, please? And you can see the agents in the beginning, they do not know each other, so that's why you see these different colors and their connections. But as time progresses and information disseminates within the network, they manage to identify each other and they start creating these clusters. And as you can see, there are two clusters of blue agents at the edge of the network. The network is not fully connected and they cannot find each other. But eventually they will. And this is going to become, as you're going to see in a few seconds, a fully connected network. This is because these groups of agents are further apart. But as I said, in the end, they manage to find each other, to identify each other. So this is how agents can connect in a social network, and you can make assumptions as to why you see these types of behavior. And this principle of homophily, we see it being used in other types of systems, like personalization and recommender systems. So if we can stop the video now. And you have come across these, but maybe you haven't realized it. When you go on Amazon, and Amazon offers you an alternative product, or it says users that have purchased this item have also purchased this. It's the same kind of principle. You identify users that have similar behavior. If you swipe your card at the supermarket records information about you. And then they use it, for instance, in my case, to give me these quarterly statements. And because they have identified that I really like chocolate of a particular type, I always get these money off vouchers for this specific type of chocolate. But I'm also getting other vouchers. And this is because their system is trying to identify other similar users with me that have purchased different products, and the company is trying to incentivize me to buy these different products and hence increase their profit. And when you're aware of these kind of applications and the information that is the data that are being gathered about you, this is okay. In some cases, people don't realize how much information we leave behind. The fact is, the amount of information and data that are going to be generated in the future will only increase. And scientists like myself are working so that we can create new methods to understand the data and then use these methods in order to provide better services and help the users with whatever daily task it is that they're trying to do. And I'm going to leave you with this question. What do you really want for Christmas this year? Do you know? My guess is Santa Claus knows, because of all the interactions that you have been doing online, all the information that you have been leaving, all the data that you are leaving behind you. So if you have been good, you're going to get a good present. It depends on the global naughty trends. Thank you.